13, day 26. Now we're looking at definite integrals. Definite integrals find values, specific numbers, not an equation with a constant like the last one. There are two methods for evaluating definite integrals by substitution. One, to find the antiderivative using substitution and then evaluate the definite integral by applying the evaluation theorem, or extend the process of substitution directly to the definite integral by changing the limits of integration. So what does that mean? The substitution formula is this. If G prime is continuous on the interval AB and F is continuous on the range of G equals U, then we have this equation. Because remember, we're saying that U is G of X. So du is G prime of X. So with this equation here, anywhere I see there's a U there, and that's a du. But now, since I'm taking into consideration with respect to the function G, that's what I'm taking the integral of, what I have to do is I have to change, because these are the bounds for the F function. The bounds for the F of X function. So all you do is take the A and B, put them inside the G function, plug A and B into G of X to get those two bounds. So whenever you use substitution, always change the bounds of integration, because that's really not what you're integrating by. All right, so let's look at example 1. We're going from -1 to 1, 3x squared, x cubed plus 1, dx. So we know our u is x cubed plus 1. So du would be 3x squared dx, which is there. So we have our u to the power 1/2 du. Now I got to change the bounds of integration. Plug those in for those. So when x is -1, -1 cubed is -1 plus 1 is 0. 1 cubed is 1 plus 1 is 2. So my new bounds of integration are those. So now I integrate 1/2 plus 1, 1/2 plus 1 from 0 to 2. Which is 2/3 u to the 3/2 from 0 to 2. But let's see, this is g of 2 to the power 3/2 over, that's 3, minus g of 0 to the power 3/2. Because the 2/3 has already gone out in front. So since this is u, 2 3/2 minus 0 3/2. Because we're integrating it with u, and these are the bounds. That's what u is. So that's 0. So 2/3. This is 1 1/2. So it's 2 to the first, 2 to the 1/2. Or square root of 2 over 3. Right? Let's look at example 2. Pi over 4 to pi over 2. You have it in front of you. Oh, good. Because these, remember, u is g of x. So these are my bounds. This is u1, u2. Sorry. No problem. So number 2 is cosecant squared theta d theta. So in this one, negative cosecant squared. So what we need here, we need a negative sign. We also have to change those. So this one is cotangent of pi over 4, which is 1, sine, cosine over sine. This one is cotangent of pi over 2 is 0. Integral of u, this is to the first power, so it's 1 plus 1 over 1 plus 1. Negative 0 squared over 2 minus negative 1 squared over 2. One half. That was A. Now B. From negative pi over 4, which is 1 tangent x dx. We did this one similar to that. Tangent is sine x over cosine x. If this is u, then it would be negative du. So I need a negative sign. So the integral of du over u is ln. Yeah, of course. I have to change the bounds of integration now. So the u function. Cosine at negative pi over 4 is square root of 2 over 2. And square root of pi over 4 is also square root of 2 over 2 in the first and fourth quadrants. Since the bounds are the same, it equals 0. Remember we talked about last time. If your bounds are the same, the integral is 0. There's no area between there. Which is last time, last section, 5.4.
Oh, okay.
Yeah. Right. Let's look at the next section. Definite integrals of symmetric functions. Whenever we talk about symmetric functions, we're looking odd versus even. Because depending on whether it's odd, this is an even function where the only thing that changes is your x from positive to negative and the y stays the same. An odd function, this is even. An odd function, when you change your x to negative x, it changes from negative to positive to negative, negative to positive. This is an odd function. So theorem 8 says, let f be continuous on the symmetric interval negative a to a. If f is even, then this symmetric integration is the same thing as from 0 to a times 2. Because we take from 0 to a and double it, we get both of those. If it's an odd function, then negative a to a equals 0. Because this part and this part cancel, this part and this part cancel. If they're odd, then they're opposites. All right, let's look at example 4 or example 3. Evaluate x to the 4th minus 4x squared plus 6. So from algebra, is this an odd, even, or neither equation? And why? What? Why is it even? Yeah, but there's a constant. Does that change anything? Functions are even if all exponents are even and it has a constant. In other words, even functions, as long as all the powers are even, it can have a constant term or not. In other words, that even functions are the only ones that integers can go into. Functions are odd if all exponents are odd. That's the only one. Cannot have a constant. That's from algebra. So since all the powers are even and it has an integer, constant terms, so that's an even function. So that means we can take our equation and we can chop it in half. Integrate each of those separately. So it's x to the 5th over 5, x to the 3rd over 3, 6x from 0 to 2. Two to the 5th over 5, 4 times 2 to the 3 over 3, 6 times 2, minus 0. All of them have x's, so they go 0. $32 over 5, 8 times 4, 32 over 3, 12. The LCD is 15. So this one multiplies by 3, this one by 5, and this one by 15. Maybe 6, 160, 180. So 180 minus 160 is 20. 20, this is positive 20. So that's 2 times 116 over 15, 232 over 15. All right. Now we get to some useful parts. Areas between curves. On your sheet, you'll see this. Well, basically, what we're looking at here is this. If we had two functions, this is f of x, and this is g of x. There's A, there's B. And if I only want to find this area here, whatever function's on top goes first, minus the one that's on the bottom. Times your width. So the area will look like this. Why do we subtract them? Because this first one, this is f of, let's say, c, and this is g of c. G of c finds this distance. F of c finds from the top down. If we get rid of the bottom, what we're left with is the middle. That's why we subtract them. So we have all of ours. So the total area is we add up all of these f minus g's times delta x's. Again, look at the Riemann sum. So let's look at this example. Did we do an example? Here's example 4. I forgot it. Example 4. The definition. Okay. If f and g are continuous on a function f of x is greater than g of x throughout the interval, then the area of the region between the curves y equals fx and y equals g of x is the difference of the two integrals, which is what we just talked about. So, example 4. Find the area of the region bounded above I 2e to the negative x plus x. Below by this curve. On the left by x equals 0, and to the right by x equals 1. So what this one looks like, it's since x is negative exponent, it's a downward graph. This is x squared over 2, so it crosses at 1/2, and it's an exponential function. This is y1, this is y2. So we're going from 0 to 1. We're looking for this area. As I said, the upper bound, this is bounded above by this function, so that's the top equation. bounded below by this equation, so it has to be between those two, from 0 to 1. I'm only looking for that area. So the total area I'm looking for from 0 to 1 is I'm going to take y1 minus y2. So that's what I'm looking at. They're each we can separate them by using the plus and minus rules. I just took each one of these, because they only separate by plus or minus. So the integral of 2e to the negative x is what? The integral of EU is EU du. Do we have, well, this is EU plus C actually. So here's E, here's our U value. So what's du going to be? -1. We don't have a negative, so we have to put a negative in front of it. So it's -2, the integral of e to the negative x dx. That one's all set. The integral of x is x squared over 2. E to the power x, derivative of x is 1. Got that? So it's e to the power x. And that's as far as that one goes. So all of these are ready to integrate. And are e to the x over 2. So -2 e to the power -1 minus -2 e to the power -0 plus 1/2 over 2, 1 over 2 minus 0 over 2 e to the 1 over 2 minus e to the 0 over 2. So -2 to e to the 1 is -2 over e. This becomes a positive. E to the 0 is 1, so it's +2. This is 0, so it's plus 1/2. E over 2. This is 1, so it's a plus 1/2. So 2, 1/2, 1/2 is 3. Minus 2 over e minus e over 2. There's your answer.
So you're so you're just going step by step to you're putting in the upper and lower bounds of each
Yes.
to
Once I
the
integrate them, I start off with the B value. So let me show you, a piece of paper. Hold on. Yeah. So once we integrate whatever we have, always start with the top one minus the bottom one.
okay.
And that's what we just did there. I did it.
Then
I
you
did.
add them all together.
Yeah, I did this one separately, this one, and then I added them all together at the end.
Okay. Alrighty.
That was example 4. Let's look at example 5 now. Find the area of the region enclosed by the parabola 2 minus x squared and the line y equals negative x. Okay, now you notice it didn't give us any other information. It just says find the area bounded by these two things. What you have to do first is find out where they're equal. Because those will be the points of your integration. So this one is 2 minus x squared, and this one's negative x. It's quadratic, so I'm moving everything over to one side, so leading coefficient is positive. And then we factor opposite signs. 2 times 1 is 2, 2 minus 1 is 1. So the 2 goes in the negative. So my bounds of integration are from -1 to 2.
Oh, okay. So if they were equal, then it would just be x equals 0. There'd be no area between them.
Exactly. And then it's from A to A.
So if you just assume that they're equal, then you'll actually find the
Oh, no, we
real.
can't because we're not assuming because we're on the same graph. So this graph here is a negative slope.
Right.
So that's y2. This is a parabola opening down, shifted up 2 spaces. So we know we have at -1 and at 2. That's where they intersect.
So
So
yeah, so equal.
we're gonna find all this area between there.
Okay.
All
And
right.
so then we integrate 2 minus x squared.
Well, now we have to integrate the two different functions. This one is y1, this is y2. So we take the top one. Well, we have a couple of them. We could do it from here to here, where we subtract them. Here, we can find all of this one, and then we can add this other one. Because you see what's going to happen here, since these values down here are negative, they're going to add to make the values the same. See what I'm saying? So let's see. we have our two equations are 2 minus x squared minus negative x dx. Two minus x squared plus x dx. We could do each one of these separately. So integral of 2 is 2x from -1 to 2. Integral of x squared is x cubed over 3. And of x, it's x squared over 2.
And then we just have to plug them in. So we got 2 times -1 minus 2
2
times.
times 2 minus 2 times
Oh,
-1.
yeah, start from the top.
It's always top down.
Minus or plus, yes.
No, this is minus here.
Okay.
Now I do
yeah.
this one. So it's 2 cubed over 3 minus -1 cubed over 3.
Plus x plus 2
2
squared
over 2 minus -1 squared over 2.
Okay. So you got 6.
2 cubed is 8 over 3. -1, so it's plus 1/3 is 9 over 3, which is 3.
2 minus 1 over 2, which is 1 point
3 over 2, yeah. 1.5, yeah. So we have 6 minus 3 is 3, plus 1.5 is 4.5. Or if we would keep it in fractions, this would have been 3 plus 1 and 1/2, or 3/2, which would have been 6 over 2 plus 3 over 2, which would have been 9 over 2, which is the same thing.
Okay, I think I get these. I think I get the definite integrals better.
Yeah,
Then-
well, and once you see that, it's the hardest part is once you get to this part, is just when you integrate each one of these separately, yeah, it's the bigger number minus the smaller number. Bigger number minus small, whatever these signs are stays there.
Right. And it seems like it's really not like once you break it down into those like the 3 integrals there, it really makes it look a lot easier, in my
Yeah,
opinion.
and I like doing it that way, but let's see, with some textbooks will give you, see, it was x squared, 2 minus x squared plus x. And then what they'll do is they'll do each one of these at the same time. So in other words, I took each of these. Now, oops, this is 2. Now they'll do the top part. Minus the bottom part. You see what I did there?
Yeah, I can see that, but to me, it makes
Yeah.
it It makes it, I think that makes it easier to make a
Mess
mistake.
up. Exactly. That's why I always like to break them up into smaller pieces.
Mhm.
But a lot of textbooks will do this. I really don't know why. I don't like that.
I just feel like it's so easy to make a mistake right there. Like you get a negative sign
Oh
wrong
yeah.
and then you're done, you know? 10
Okay,
minutes
so
will come.
yeah. So far today we talked about we use substitution. So whenever you use substitution and you change the from dx to du, you also have to change the bounds of integration. This is from dx to du. All right. So that's when we first started discussing this stuff during substitution. Now we learned when you have two functions, y1 and y2. So this is y1, this is y2. Whatever is on top will be always what goes first. It's bigger minus smaller. So that way you never end up with something negative. And what you always want to do first is to see if there are any points in common. Set them equal to each other. Solve for the x's, and those become your x1 is your A, your x2 is your B. So far, so good.
Mhm.
Now we're going to take something, we're going to flip the world on its side. You notice how, remember, if we're looking at the Riemann sums, we're adding up all these little slivers, right? This one and this one, this one.
Mhm.
What if instead of this way, what if we want to go this way now? Integrate with respect to the y-axis. We're now going to do horizontal integration. Up until now, it's always been vertical. So
So
if we had,
your bounds are going to be y variables.
yep, you can go from y1 to y2. This is A and B. And so your area formula, I'll call C and D so it doesn't get mixed up with A and B. Now our area is going to be looking like this. This is horizontal integration with respect to the y-axis. So let's look at an example here. It says, find the area of the region used in example 6. Example 6 gave us these. Find the area of the region in the first quadrant bounded above by y equals radical x and below by y equals x minus 2. So let's look at that graph. Radical x looks like this. x minus 2. It looks something like this. So in example 6, we're taking, this is y1 and this is y2.
So we're looking for our upper and lower bounds. And the way we do that is by setting root x equal to x minus 2.
Well, yeah, root x can't be negative, so it has to be greater than 0. And where these two intersect. This is still example 6. So we have to get rid of the radical, so we square both sides. This is x minus 2 times x minus 2, which is x squared minus 4x plus 4. Oop. Make it equal to 0, so I subtract x. They're both the same. They're both minus. So what times what is 4 when you add them? You get 5, 1, and 4. So x equals 1 and x equals 4. So we're going to use the 4. Because that's where they both intersect. So this one's when x is 4, y is 2 at that point. So that's how we used to do it. Now we switch and use y. So here we have y equals radical x, y equals x minus 2. We first have to solve both of those. This first one, y squared equals x. This one is y plus 2 equals x. Okay, now we're looking at it. Now our integration now we're looking at it this way. It's going to go from 0 all the way up to this one. So our bounds of integration are going to go from 0 to 2.
Okay.
Now we set up our functions. Since we're looking at it on the y-axis, which one's on top? Is it y1 or y2? Remember, we're looking at it this way now. So y2 is on top. So we have to take y2 minus y1.
Do you always have to swap it like that?
Yes, because not only do we change the x and the bounds of integration, but now instead of the top one being top over here, it's now the bottom one.
Wait, so why are we using 0 and 2 as our bounds of integration and not 1 and 4?
1 and 4?
Mhm.
Oh, because 1 and 4 are between, I mean, 0 and 4. That was used for our DX.
Okay.
It's not 1 to 4, it's 0 to 4 because the radical X starts at 0 and goes on.
Okay.
So the bounds are going to be from 0 to 4. But now since I changed it over here, I'm going from this one, which is 2, all the way down to as far as it can go is at 0. So I
Okay.
can only use these numbers.
Okay.
So far, so good. Because that's just, we're just now still just setting it up. So our area is going to be from 0 to 2. The second equation, this one is y plus 2. And this one is y squared. So we do y plus 2 minus y squared. Y sub 2 minus y sub 1. With all of these, we could just break it up. And take it with that bound. So the integral of y is y squared over 2. Two is 2y. And y squared becomes y cubed over 3. Remember, we have to add 1 and divide by that. So since our bottom bound is 0 and they're all with respect to y, we don't have to worry about the zeros. So all we have to do is the top number. 2 squared over 2. 2 times 2. 2 cubed over 3 minus 0. So this is 2, so it's 6 minus 8 over 3. Common denominator is 3, so it's 18 over 3 minus 8 over 3 makes it 10 over 3. And that does it for the semester. Woo, doggy.